Today we'll learn how to build an artificial neural network model using the PyTorch framework. If you want to learn how to use it to predict which Titanic passenger survived the disaster, stay with me. I'll show you how to create and train such a model on real historical data from the most famous maritime disaster. Let's get started. Before we dive into the code editor with enthusiasm, you might be wondering, what is PyTorch? It is a powerful tool that makes it easier to build machine learning models based on neural networks. It provides many ready-made modules, classes, and functions that are building blocks for such models, and also helps with handling data like images or audio recordings. It is currently one of the leading frameworks for deep learning, right alongside TensorFlow. For example, the PyTorch repository on GitHub ranks second in terms of stars received. But let's move on to neural networks themselves. As you may know, at the core of how neural networks operate lie computationally intensive mathematical calculations, more precisely matrix operations, and we can basically split them into two stages. One is the feed-forward, where the input of a layer is matrix multiplied by the layer's weight vector, and a result goes through the so-called activation function to finally reach the input of the next layer. The process repeats until the computations reach the last layer, and its outputs are the model predictions we're after. The second phase is backpropagation, during which we make corrections to the network parameters, the weight values of each layer based on how much our prediction differs from the true value. This process, in a simplified form, runs from the last layer to the first and tries to compute the weight updates according to their partial contribution to the error of our prediction. In this process, the gradients of the weights, vectors of partial derivatives, are calculated. In this context, the PyTorch tensor object comes into play. You can think of a tensor as a multidimensional array on which you can perform various operations and transformations. It simplifies the operations that lie at the core of all neural networks, and it also has a built-in mechanism for computing gradients. So this is a good place to take a closer look at how they operate and on what principle. Let's switch to Visual Studio Code to see PyTorch in practice. We'll start with tensors. For this, we need to install the Torch package. For the purpose of this tutorial, we'll also add a few extra Python libraries. It's best to create a virtual environment, activate it, and use this command to install all the packages. I've already done this step, so we can jump straight into the notebook. First, let's import the Torch package. Let's now create the simplest tensor that is truly zero-dimensional, which means a scalar. For clarity, we'll also check its dimensions using the shape attribute. As you can see, it's simply a number. Ultimately, our goal is to store multidimensional data arrays and perform calculations on them. A good example is a 2x2 tensor. On such a tensor, you can perform various mathematical operations. For example, adding, multiplication, transposition, which swaps rows with columns and plays a key role in matrix operations. But let's go back to our example with a scalar. This time, though, we want our tensor to have an additional property. It will be able to track gradients. For this purpose, when creating it, we will pass the value true to the requires grad parameter. In fact, tensors store data in the data attribute. They also have a egrad attribute which stores gradients, the values of partial derivatives. They play a key role in the backpropagation process in neural networks. Soon we'll see how to compute them. For now, ggrad doesn't store any values. An operation on a tensor will return the result as a new tensor. This one, in turn, can be used for subsequent operations. This gives rise to the so-called computational graph, which offers us a particular capability, namely, computing gradients by calling the backward method. Of course, obtaining gradients is possible only for tensors for which requires grad has been set to true. This functionality is one of the key elements in building neural networks in PyTorch. So let's get back to our task. Before we start building our neural network in PyTorch, let's add at the beginning a few imports that we'll need. The most important thing, of course, is PyTorch. I import the entire package as torch, and for defining models, I also use the NN module. For data work, I'll also use dataset and data loader, which will help us conveniently load and prepare the data for training. In addition, you'll find pandas useful for working with tabular data and tools from scikit-learn for splitting the dataset into training and test sets and for standardizing the data. Finally, I also add matplotlib and seaborn, which will be used for visualizing the results and presenting charts. The first thing I obviously need is data. Luckily, the Seaborn library provides a ready-made dataset that we'll use in our project. It's enough to use the load dataset function and specify the dataset name in the parameter. The dataframe object has all the data we need and even more than we need. In practice, we won't use all of them. Let's limit ourselves to just a portion. In the variable description, I'll store their description so that if needed, we can easily refer back to them. We'll rewrite our data table, keeping only the columns that I consider contain the most meaningful data, such as ticket class, passenger gender, age, number of siblings, number of parents, ticket fare, port of embarkation, and passenger category. We will also keep the survived column, since it is our target value that our model will later predict. Next, we will move on to cleaning and preparing our data. In this case, we will fill missing values of age with the mean. In the sex column, we will replace the strings with numeric values 0 and 1. The columns embarked and who are categorical values, and therefore we will write them in the so-called form, one-hot encoding. Pandas offers us a ready-made function getDummies, which returns a process data frame containing additional columns with 0 and 1 values indicating whether a given element belongs to that category. Additionally, we will ensure that these ones and zeros are actually numbers instead of text. Finally, we'll split our table into the so-called independent variables, traditionally written as x, and dependent variables as y, which we want our model to predict. Y contains only one piece of information, whether a given passenger survived the disaster or not. If anyone is wondering why I chose to select some columns and skip others, and why I perform such transformations on certain columns and not others, the answer is quite simple. I've already familiarized myself with the data and their format. This is a key element of the data cleaning process, which I'm skipping here because otherwise this video would be too long, and I'd rather keep your attention on the main topic of building a neural network model. Having our x and y values, we need to split them into a training set and a test set, which we will use to evaluate the quality of the predictions from the already trained model. This is such a common practice that there is a dedicated function, train-test-split, which we have already imported. Another practice that typically improves training performance is scaling the input data. The input data are often expressed in different units and across different orders of magnitude, tens, thousands, or even millions of units. Scaling will ensure that each feature has a similar contribution to the prediction outcome. For this purpose, we instantiate a standard scalar object and then fit it to the training data and scale them at the same time. We also scale the test data. At this stage, we already have the data prepared and split into two sets, the training set and the test set. Before we proceed to building the model, we will use the standard way of wrapping the data using the dataset and data loader classes belonging to the PyTorch framework. Generally, this provides a consistent and customizable way of loading data into the model. We will create a Titanic dataset class that requires us to define the length of the dataset using the len method and how to retrieve data at a given index. The next step will be to instantiate the appropriate datasets and, based on them, create data loader objects where we specify the batch size. For the training data, we will set the shuffle parameter to true to randomly shuffle the order of the data in each training epoch. In summary, the data loader provides an efficient way to fetch data from the training and test datasets. At this stage, we have finished working with the data. It may seem a bit complicated or require too much unnecessary effort, but this approach provides a universal pattern for working with data that we can adapt to our needs. A good example of applying this approach could be a large set of images that will be gradually loaded into memory during training in successive batches. Storing all images in RAM could prove impossible due to limited hardware resources. Now we can proceed to building our neural network model, Titanic model, which inherits from the model class that is part of PyTorch. Within our model, we need to specify two things. What layers and components make up our neural network, which we'll define in the init method, and how the invocation of this model on the dataset proceeds, which will be defined in the forward method. The model will need to accept the input size in its constructor. In the init method, we will create 3 linear layers, specifying for each the number of inputs and outputs. The number of outputs of a layer equals the number of inputs of the next layer, which corresponds to a full connection between the layers. The last layer has only one output, since it will correspond to the predicted value indicating whether the given passenger survived the Titanic disaster. Neural networks, however, before passing data to the next layer, pass them to so-called activation functions which transform them. We will use 2 of them. One of them is rectified linear unit, which returns 0 for negative argument values or the argument itself otherwise. The second is the sigmoid function, whose values lie in the range from 0 to 1. It will be applied to the output of the last layer, whereby a result close to 1 will be interpreted as a passenger who survived the disaster, while 0 as the opposite. The forward method defines how information flows through the model. The input data first goes into the initial layer, then through its activation function, and is passed on to the next layer. For the first 2 activation functions, separating the linear layers, we'll use ReLU, a very common choice in many models. The last activation, however, defines the range of the model's outputs. That's why it must be chosen according to the problem and the type of data we expect. In our case, we want a binary result, 0 or 1. For this reason, the final operation in our model will be the sigmoid function, which meets these requirements. Finally, we instantiate the model object, passing the data size in the input size parameter. The parameters of this model are stored as tensors within the successive layers. This, however, will change during training. They will be optimized based on the network's prediction errors. To enable the learning process to take place, we also need 2 more elements. Loss function, which determines how the prediction error is defined, as well as optimizer, which is responsible for adjusting the network parameters according to a specified strategy. We will use the loss function, binary cross-entropy, which is designed for binary classification problems, where the model's output serves as the probability of belonging to one of the 2 categories. As the optimizer, we'll use Atom, which dynamically adjusts the learning rate. It works well in most cases. The optimizer takes as an argument the model parameters, which it will modify, and the learning rate, which is the base learning speed. We don't need to define them ourselves. They are part of the PyTorch framework and widely used in the world of machine learning. Finally, we can define a training function for the model, train epoch. It will correspond to a single training epoch. The function operates on the model and the dataset loader. First, we set the model to training mode. This slightly changes the model's behavior in certain aspects, such as the dropout layers. Additionally, we create 2 variables. Total loss, which will store the epoch's total loss, and correct, which stores the total number of correct predictions. At the start, both variables are equal to 0. Next, we create a training loop that iterates through the loader, pulling in whole batches of input data and their corresponding values in IT. The inner part of this loop is crucial for understanding the learning process. Let's look at them step by step. 0 grad zeros all gradients of the model. This is an important step because, by default, the gradients of tensors in PyTorch accumulate every time they are computed. The next step is performing the model's predictions on the entire batch of input data. The result is a series of predictions with length equal to the batch size. In this case, we remove one dimension from the tensor using the t-squeeze method, so that it matches the shape of the batch wibe. Our predictions take the form of probabilities in the range from 0 to 1. Any value above 0.5 is treated as a prediction of 1, the rest as 0, and we convert them back to the float type. Thanks to this, we'll be able to compare them to the true answers y. Here we compare our predictions predicted with the actual values and sum the number of correct predictions in the batch. The item function lets you fetch a plain number from a tensor rather than a tensor with a single value. Then we compute the error of our prediction using the previously chosen loss function. The loss shows how much the model's predictions differ from the true values. The lower the loss value, the better the model fits the data. Calling backward triggers the computation of gradients for all tensors that were involved in calculating the loss value. This allows PyTorch to know how to adjust the model's parameters to reduce the error in subsequent training steps. Calling step on the optimizer modifies the parameters stored within the neural network's layers based on the gradients calculated in the previous step. This is where the network learns. At the end of the iteration, we add the current batch's loss to the total loss. The loss returns the average loss per example in the batch, so to obtain the total loss for all examples, we multiply it by the number of elements in the batch. After going through all batches in one epoch, we compute the final average loss (averloss) and the prediction accuracy for the entire dataset. The function returns these two values, which we can monitor during training. The next function we need is the evaluation function eval model. It will help us assess the effectiveness of the already trained model. Basically, it is structured similarly to train epoch, with a few key differences. We put the model in evaluation mode, which disables certain training-specific behaviors. Next, we reset the total loss counter and the count of correct predictions for this evaluation. The torch no-grad block disables gradient tracking. As a result, evaluation is faster and uses less memory. In the with block, we iterate over all data batches in the test loader. For each iteration, we perform the same operations as those we saw in the training loop. We make predictions, tally the number of correct predictions, and compute the loss and total loss. This time, however, we are not training the model, we're just using it. We do not update gradients with the backward method and do not modify the model parameters with the optimizer step method. After iterating through all batches, we compute and return the average loss and the accuracy for the entire test set. Finally, we can move on to the most important stage, namely the actual training of our neural network using the train epoch function. We create two empty lists in which we will record for each epoch the loss and accuracy. In the loop, we train the previously created model for 500 epochs, printing loss and accuracy to the console, which allows us to monitor progress in real time. Once our model has learned, it's worth seeing how the entire training process unfolded. The simplest way to do this is by plotting charts. On one, we show how the loss value changed, and on the other, how the prediction accuracy grew across successive epochs. To plot these charts, we use the matplotlib library, which allows us to visualize the results of our training. In this snippet, I use the 8subplots function, which lets me create a chart with two axes so I can show two different metrics simultaneously, loss and accuracy. The plot function draws the linear progression of both values over successive epochs, while Twinks allows me to overlay both plots on a single diagram. Finally, I describe the axes and give it a title for readability. Additionally, thanks to the siteTideOut function, all elements of the chart are arranged properly. Let's quickly run our script and see the model in action. During training, we'll watch how accuracy and loss change step by step, and at the end, we'll check the plot with both curves side by side. What we can see on this plot is a rapid drop in loss and a sharp rise in accuracy at the beginning, followed by flattening curves where improvements slow down in the later epochs. At this point, I can comment out the matplotlib code that plots the charts, since we've already seen them, and move on to applying the model. Now let's use it to predict the survival chance for a single passenger from the test set, the simplest way to see how it works on real data. First, we randomly select one passenger from the test dataset. To do this, we will import the drandom module from the Python standard library. We fetch the passenger's data and prepare it in the format the model expects. We convert it to a tensor and add the batch dimension using the unsqueeze method. We also record the true label, whether the passenger survived or not. We switch the model to evaluation mode and make a prediction. Here we obtain the survival probability and the model's decision, and finally compare it with the actual outcome for this passenger. So here's the full script in action. Training runs, the prediction is made, and as we can see, in our case, the passenger survived. That's all for today. I've shown you how to build and train your own neural network from start to finish, using a practical example of the famous Titanic problem. If you found this material helpful or learned something new, I'd really appreciate it if you left a thumbs up or shared the video with someone who might be interested. Do you want to see more projects like this, or do you have an idea for the next topic? Subscribe to the channel and comment what you'd like to see next time. Thanks for watching, and see you in the next episode.